Assalamualaikum, sir. We are from Group 8. So today we are going to present our project titled Classroom Participation Gesture. This project focuses on using AI and post detection to recognize student participation gesture in real time using a webcam. So we move on to our project background. For this project, in 2025, technology in education has increased rapidly, making smart classrooms once common. However, teachers and lecturers still monitor student participation using manual methods such as watching for raising hands or calling out their names. This method can be time consuming, inconsistent, and difficult to manage, especially in large classrooms. Nonverbal communication, such as body posture and hand gesture, is also an important indicator of student engagement and attention. But it is not very easy for educators to continuously track this gesture while teaching. Therefore, this project applies artificial intelligence and computer vision to recognize classroom participation gesture automatically. We use Google Teachable Machine to develop a pose-based classification model that focuses on body movement instead of facial features. This approach supports privacy while helping teachers monitor student engagement in a more objective and consistent way. Next, our objectives are to design and train a pose-based gesture recognition model using Google Teachable Machine, real-time gesture recognition using the trained model. Lastly, this project evaluates the feasibility of using post-based machine learning to support objective classroom participation monitoring. And in terms of scope, the system uses post-landmark data captured through a laptop webcam, such as arm, shoulder, and body position. Facial features or personal identity data are not collected to ensure privacy and ethical data usage. The model focuses on three gesture classes: raising hand while seated, standing to ask answer a question, and sitting in a natural posture while listening. The target users include lecturers, students, and educational institutions interested in smart classroom technology. The project is developed and demonstrated using Google Teachable Machine and a laptop webcam for a real-time testing. For the project significance, this project is significant because it helps teachers understand classroom engagement in a more objective way instead of relying on manual observation. The system uses posture and gesture to identify student participation more consistently, especially in large classrooms. It also supports smart classroom development by using post-based AI with simple and low-cost tools while protecting privacy because it does not use facial recognition. For the expected outcome, the project will produce a trained model that recognizes three gestures: raising a hand, standing, and sitting while listening. The system will demonstrate near real time using a laptop webcam, showing the predicted gesture and confidence score. Next, we move on to solution design.
Okay, let's start with the solution design. First, from a system overview perspective, the system is designed to recognize classroom participation using post-based artificial intelligence. Instead of using facial recognition, the system focuses on body posture and movement, which helps to ensure privacy preserving and ethical classroom monitoring. The system operates in real time using live webcam input and supports three classroom gestures, which is raise hand, standing, and sitting. Moving to the system design flow, the process begins when a student performs a classroom participation gesture. The webcam then captures real-time body posture and movement. This input is analyzed by the pose-based gesture model, which focuses on body pose and joint positions. Next, confident classification is performed, where the system selects the gesture with the highest confidence score. Finally, the recognized classroom gesture is displayed as the system output, either a raised hand, standing, or sitting. Overall, this solution design provides a simple, real-time, and privacy-aware approach for recognizing classroom participation gestures. Let's move on to the implementation.
For the implementation part, I will explain how our classroom participation gesture system was actually developed and executed in practice. The system was implemented as a proof of concept using a post-based machine learning approach. The main goal of the implementation is to demonstrate how classroom participation gesture can be recognized in real time using a webcam without relying on facial recognition, which helps to preserve user privacy. In terms of tools and technologies, we use Google Teachable Machine with the post model features. A laptop webcam was used as the main input device to capture live video. The system runs in a browser environment, so no additional hardware or complex setup is required. This makes the implementation low cost, simple, and suitable for classroom environment. For post data acquisitions, the system captures live video input using the webcam. Instead of analyzing facial features, the model focuses only on body landmarks such as arm positions, shoulder alignment, and overall posture. Users are required to stand or sit within the camera frame so that major body joints can be detected clearly. This approach allows the system to analyze participation behavior while maintaining privacy. Based on the project scope, three classroom participation gestures were implemented. The first gesture is raise hand, which represents a student raising one hand while seated. The second gesture is standing to ask question, where the student stands upright. The third gesture is sitting and listening, which represents a student sitting attentively in a neutral posture. Each gesture was trained using multiple samples to help the model learn variations in body posture. The model training was carried out using a Google Teachable Machine. During training, the post key point detected from the webcam were converted into numerical data that represent spatial relationship between body parts. A neural network classifier was trained to distinguish between the three gesture classes. Teachable Machine automatically handles features extraction and optimizations, and the model produced confidence score for each predicted gesture. After training, the model was tested in a real-time environment. The webcam continuously captures video frames and post-estimation detects body landmark. The trained model then processes the post data and generates confidence score for each gesture class. Finally, the gesture with the highest confidence score is displayed as a system output. This shows that the system can recognize classroom participation gesture live and continuously. The system was tested under control conditions to ensure consistent performance. These conditions include good lighting, proper camera distance, and full upper body visibility. When these conditions were met, the model produced high confidence scores and stable prediction for all gesture classes. However, there are some limitations observed during implementation. Poor lighting conditions, incorrect camera distance, or incomplete gesture can reduce predictions confidence. For example, a partially raised hands or slouching posture may affect recognition accuracy. In addition, the system is currently limited to only three gesture classes as defined by the project scope. I think that's all. Let's move on to the next part.
For the result and analysis, the post data used in this project was captured through a laptop webcam using Google Teachable Machine. Instead of raw images or facial features, the system extracts post landmarks such as head position, shoulders, arms, and body alignment. First is rest hand. For the rest hand gesture, the model achieves 100% confidence under optimal testing conditions. This occurs when the user's arm was fully raised and clearly visible within the camera frame. Next is standing to ask question. The standing to ask question gesture was recognized with high confidence when the user transitioned from a seated position to a fully upright posture. Changes in body height allowed the system to clearly distinguish this gesture from seated poses. Sitting and listening. The sitting and listening gesture was correctly classified when the user remained seated with minimal movement, while this gesture produced slightly lower confidence values compared to more active gestures. The prediction remained stable and consistent. Testing was conducted by following the tips provided in the Teachable Machine interface. This included lighting conditions, full upper body visibility within the webcam frame, and proper distance between the user and the camera. However, when the user moved too far from the camera, some body landmarks were not detected clearly, causing confidence level to drop below 100%. Similarly, poor lighting conditions reduced post visibility and affected prediction accuracy. The result from the analysis confirmed that post-based gesture recognition using Google Teachable Machine is suitable for classroom participation monitoring. The system performs best when gestures are clearly executed under proper environmental conditions.
In conclusion, the classroom participation gesture POSE system shows that POSE-based machine learning can be used to track student participation in real time. By using Google Teachable Machine, the system was able to recognize simple classroom actions like raising a hand, standing, and sitting with a good accuracy. Since the system focuses on body movements instead of facial recognition, it helps protect student privacy and makes it more suitable for use in the classrooms. However, the system accuracy can be affected by factors such as lighting, camera position, and distance from the camera. Even with these limitations, it is still a low cost and non-intrusive solution that can be easily used in modern classroom. Overall, this project acts as a basic proof of concept for smart classroom systems. And with further improvement like adding more gestures and improving performance in different environments, it has the potential to support educators in monitoring students' participation more effectively. So we move on to the demo part.
Next, I will demonstrate the dashboard for our classroom participation gesture system. First, I start the webcam by clicking the Start Camera button. This system begins capturing live video input from the webcam. As you can see on the screen, this system detects Fiona body pose using pose landmarks, which represent Fiona head, arms, and body position. This confirms that the webcam input is working correctly. Now, I will demonstrate the raise hand gesture. When I raise my hand clearly within the camera frame, the system recognizes the gestures and display raise hand with a high confidence score. Next, I demonstrate the standing gesture. When Fiona stands upright, this system detects the change in body posture and correctly classify it as standing. After that, Fiona will demonstrate the sitting gesture. When Fiona sits in a neutral position, the system recognizes this as sitting, indicating attentive listening behavior. On the right side of the dashboard, the system selects the gesture with the highest confidence score as the final output. This demo shows that the system is able to recognize classroom participation gestures in real time using pose-based analysis without relying on facial recognition, making it suitable for privacy-preserving classroom environment. That's all for our demonstration.
Thank you,
Thank
Thank
sir.
you,
you.
sir.
Bye.